Recording is rolling. It is Friday, September 20th. So we're going to revisit this mystery cup from yesterday. Then we're going to continue with free body diagrams. That's what FBD is, free body diagram. You guys remember yesterday, the last half of class, we were going through this PowerPoint, we are doing a bunch of different scenarios, free body diagrams. We're just going to do more of those. Today's a little bit short day, so we're going to get as far as we can today, right? All right. So here, this mystery cup. Remind you guys from yesterday what this was. It's like, okay, that looks like a perfectly normal cup. There's nothing wrong with it. Well, hold on. Wait, what's the hole in the bottom? Oh, there's a little straw poking out. Turn it around. Okay, I see another straw there. I wonder if these straws connect somehow. Well, let's try it out. So then I filled it up halfway with water yesterday, and it held the water perfectly fine. Well, at least I know it's not a straight shot connection. It's got to be something more than that. It works pretty fine. But then I filled it up to the brim. And then the water was leaking out the bottom. In fact, the entire cup drained. And the puzzle question for you guys was, how exactly is the straw connected on the inside? What is the straw doing that makes it work like that? Okay, so moment of truth. See who's figured this out over the last 24 hours. Who thinks they got this figured out? Anybody at least got a guess maybe how this works? What's going on? What do you think? All right. Yeah, at least figured it out. Yeah, that's exactly it. Here, I'll show you guys. I actually have a poster for this. I don't know if you guys downloaded the whole book, but this is one of them. Aha. So it's called Pythagoras cup. That's exactly it. So yeah, the straw just goes up the side. Okay, so let's walk through step by step. See, like first I filled it halfway with water. A little bit of water goes into the straw, but it just kind of stopped right there. Just holds water. Now, if you fill it to the brim, this whole straw is going to flood. And then, okay, now we got a connection with the bottom. Now the water starts to flow at the bottom. Okay? But when the water level goes back to the previous level that it was fine at before, now there's a state change. This and this are different. Now, you guys see the water floods the whole straw on the inside? You said too? Right? Right. Now, okay, so it's all going to get siphoned out. If you look under your sink, you might see a pipe that does something like this. If you look at the back of your toilet, I bet you see a pipe that does that too. It's like the siphon. That's how these work. Right? Now, part of what makes this work, I think I may have mentioned yesterday, is the fact that we're in an atmosphere. But here, guys, how about this? Suppose you had some material that was able to be a liquid inside a vacuum, and you tried this. Guys, would this pump actually work in a vacuum? Would this work in a vacuum? No. Here's why. When it gets to this state right here, what would happen is whatever liquid that could somehow exist in a vacuum would actually split, and part would fall left and part would fall right, and then it would just stop right there. It would stop. So, but the whole thing wouldn't get all siphoned out. Right? So you do need an atmosphere to make this work. Do you guys remember from yesterday? What is one atmosphere of pressure? What's another way to quantify that? How many pascals is that? 100,000? 100,000? Okay, like 101,000 something? Yeah. Here's where 1 pascal is. Here's 1 Newton of weight. If you put this on a 1 square meter foam board, 1 Newton on 1 square meter, that would be 1 pascal. We have 101,000 of these acting on us right now just from the atmosphere. Right? So back to this Pythagoras cup. Right? So the fact that we're in an air pressure allows us to work at all, but we are in a finite pressure, although it's a huge pressure, but it is finite. Right? I wonder how big this cup could possibly be to still continue to work. Like here, suppose you're like driving around on the interstate, and then you see off to the side of the road the world's tallest Pythagoras cup. The world's tallest Pythagoras cup. Like, wow, I gotta check that out. So we're gonna see it. So you pull over and check this out. Right, guys, how tall could this possibly be and still function? Does anybody know that? Does anybody know? All right, give you guys a hint. Give you guys a hint. Suppose you go to a really deep pool or a really deep lake, and you dive down into the really deep lake. You keep diving. Can you guys feel as you guys dive deeper, deeper, deeper? You guys feel the pressure going up? Feel the pressure going up? Get more and more pressure. Okay. How deep do you have to dive to effectively double the pressure? Like at the surface, we're all sitting at 1 atmosphere in this room right now. Okay. And then you dive down into a pool, and I feel the pressure going up. Got like 1.1 atmospheres, 1.2, 1.3. At some point, I'm going to hit like 2 atmospheres, right? One from the actual atmosphere, one from the additional water depth, right? How deep do you have to go to get the additional atmosphere of pressure? Does anybody know that? Turns out it's about 10.3 meters deep, about 10.3 meters. That's like 30 something feet. You're saying, right? Right? And it turns out if you just reverse that and turn it up, if you have a straw, suppose you have a straw that's like 10 meters long and you dip it in the water, that's about as long a straw as you could possibly get to work too because of our pressure differential. People were discovering this a few hundred years ago when they had like towns sitting on top of hills and there was like a lake way down below. They had let's start pumping up that water. So they had some first pump and pipe systems. They realized they could only pump up about 10 point something meters and then it would run out. And do you guys know what water does when the pressure runs out? What does water do in a vacuum? Starts with a B. Boils. It boils, right? And it doesn't boil because it's hot. Like you can say, that's boiling water. If you touched it, it actually wouldn't be hot. It would be room temperature. And if anything, actually, it would be cooling down because boiling is a cooling type process. We'll talk about this probably in February. I think we'll get to, right? But yeah, that's what it would do. So if you had like a 10-meter long straw, you start drawing the water. At some point, the water is going to boil away, right? Because that would be the tallest type Pythagoras cup you could use. Of course, this cup is much, much shorter than that. So there's no problem with this one working. All right, so you guys good on Pythagoras cup? All right, let's do free body diagram time. Free body diagram. Before I do the PowerPoint version today, I want to go back and revisit an old situation. Right, fill in some details. Right, so what I have here is called projectile. Do you guys remember? Here's an old pair of posters. You guys remember this pair of posters from like a week or two ago? This cannonball projectile. You guys remember that projectile? Right. Now I think some of you guys may because I know some of my classes students were asking me about this. They said, "Hey, what does this note mean right here?" Note, not a free body diagram. So we'll talk about that in the future. Oh, well, now's the future because now you guys know what a free body diagram is. Guys, a free body diagram, you're labeling what type of vectors? Force vectors. Force vectors. And for now, only force vectors, right? Guys, are velocity vectors part of free body diagrams? No, right? But let's go back to this pair of posters. Guys, what type of vector is this here and here? What type of vectors are these? These are what's meters per second? Is that a velocity vector? Yeah, guys, these are all velocity vectors. Isn't that true? Okay, that's why it's not a free body diagram because these are all shown as velocity vectors. This is the velocity of the cannonball. Okay? I wonder what the free body diagram actually would look like for that situation. Are you guys ready for that? Right, so you guys got your notes out. Everybody got some notes out? Here, we got some paper around. Okay, so looks like my stools are out of paper here. Okay, so everybody's got some paper or some notes. Just got some paper, some notes going on. You guys got all right. Everybody's got paper and notes. And so let's do frame by frame that cannonball flying through the air again. Except I want to make a free body diagram out of this. Go ahead and write in your notes. Right, free body diagram for a projectile. Projectile. Okay, which here I'm gonna make that style I just had on that poster. So let's say you have a cannon down here at ground level. You're gonna angle it up, blast the cannonball, and then so the first frame is gonna be after the cannonball has left the cannon. So the force from the cannon is already over and done with. Right now the cannonball is just set into motion. It goes. Right, follows a nice parabola path, right. So because of the projectile parabola path. Okay. Let's say I take a picture every second about. So right, and now that was right before it hits the ground. So right after it's left the cannon barrel and right before it hits the ground. You see that? Okay. Now if I drew this correctly, I think I got pretty close. Right. Do you guys see how horizontally these are spaced out evenly? Right. And that would be true. You guys remember that from about a week or two ago, right? Like horizontal velocity is constant. But do you guys see vertically? It looks like it's like slowing down on the way up and it's speeding up on the way down. Okay, that's just review from like a week or two ago. Okay, you guys know that already. But we're not interested in velocity so much right now. We're interested in what kind of vector again? For free body diagrams? Force vectors, force vectors. Go ahead. Let's see. I wonder what the force vectors look like on this free body diagram. Well, we're going to do one for each frame. Okay. Let's start with the right at the very top. Okay, guys, right at the very top. Is the cannonball moving horizontally? Right, for one instant, it's only moving to the side. Now that's motion, that's velocity. Okay? Now I'm going to put a center mass dot on that cannonball. I'm going to draw a force vector on it. Or maybe more than one force if there's more than one force, or maybe just one force if there's only one. Right? Free body diagram, forces. Is what's one force that is definitely acting on this cannonball right here? Gravitational force. Can you guys draw a downward arrow and label that? Ooh, what have I been labeling for weight? mg could be weight, right? Or I'll say or F sub g, or if you just want to write out the word weight. Those are all the same thing, right? Mass times gravity field, force due to gravity, weight, right? There's 3 different ways to write the same thing. Okay. All right. Okay, so gravitational force, definitely pulling it down. Now, most of the time for these type projectiles, we've been ignoring air drag. Have we been doing that? Just ignoring air drag? Okay, so let's do that for now. Okay, so there's no air drag force because we're just saying it's negligible if it exists at all. Okay. Is there any other force then on that cannonball? No, that's it. That's the entire thing. That's the entire thing. You're done. If I say draw the free body diagram for that cannonball right there, that's the only one. Just weight, nothing else. Okay. What about, let's do the other ones. What about right here? What's the forces right here? Okay, so gravitational force, weight, I can down. Is it the same weight as before? Is it the exact same weight? It's the same weight, right? Any other forces? Nope. How about right here? mg. How about right before it hits the ground? mg. How about right here? mg. How about right here? mg. How about right after it's left the cannon? Right, so again, the cannon's done pushing it, right? It's starting to coast now. mg. Right. There it is. So there's 7 different free body diagrams while it's in motion, but they're all the same. All the same, right? Notice its direction of motion is changing, its speed is always changing, it's slowing down on the way up, it's speeding up on the way down. That's all the stuff we did a week or 2 ago, right? But the force is always the same. There's only one force, just its weight. That's it. Right, you guys got that? Makes sense? Okay. Let's say I want to do a step more complicated. You guys want to do? Okay. What if we did consider air drag? You guys ready to consider air drag a little bit? Air drag, right? Here I'm going to start right at the top for air drag. Right? You guys remember the ball's moving to the right. Guess which direction the air drag points? To the left. Do you guys think drag force is always going to oppose the direction of motion? Right? Okay, so I'm going to draw, I'll make it kind of small. I bet it's pretty small compared to the weight of the cannonball. I'll do F drag like that. Right? So pretty small compared to the weight of the ball, and opposite of the motion of the ball is trying to slow it down. Sort of. How about right here? Which way does drag force point? If the ball's moving down to the right, the drag force is probably pointing up and to the left to resist that. Yeah, guys think? Oh, and maybe the fact that it's speeding up a little bit, I'll make it a tiny bit bigger than this other drag force. Do you guys think drag force is like the faster it's moving, the more the drag force? You guys think? Okay. Okay. F drag. Okay. How about here? F drag. How about here? F drag. How about here? F drag. Here. F drag. And here. F drag. Be like that. Yeah. Okay. Which again, more often than not in this class, we just ignore that one because okay, that's kind of small compared to its weight. It's negligible. We'll just ignore it anyway. Right? But if you did consider it, right? I mean, maybe it was a ping pong ball, you definitely have to consider it, right? Okay. All right. So you guys good with free body diagram for a projectile? All right. All right. You guys ready for PowerPoint time? It's about to be the PowerPoint time. All right. So in your notes yesterday, I think we left off approximately on the slide. Did we do? So here, let's hit this one more time and then we'll go on to new stuff. So we were looking at some pretty fundamental type free body diagram situations yesterday. Right? And we got to a rocket moving at constant velocity, 10,000 meters per second in deep space. There's no significant gravitational forces nearby. It's just screaming through space, constant velocity, 10,000 meters per second. And what forces did you guys put on that rocket yesterday? None. No forces. Wait, is that it? Are you done? Is that the entire free body diagram? That's it. Guys, don't draw anything on that rocket. You're done. There are no forces. No forces. Right? Oh, isn't that kind of like Voyager spacecraft? It's just coasting. It's just going. Right? Oh, here's maybe how you can kind of get to that too. Guys, constant velocity. What do you know about constant velocity? What does that mean is acceleration equal to? 0. If there's no acceleration, what do you know about the net force? What is the net force equal to? Yeah, 0 newtons, right? And in this particular case, if you're in deep space, you just don't need any forces at all, right? You're just coasting, right? I got another question for you guys. What if you're inside that rocket? What does that feel like? I'll give you guys a couple of options. Option A, do you feel like you're thrown back against your seat, like, I'm being pushed against my seat so hard? Or option B, are you just floating around like you're just floating in deep space? Which one of those is correct? Option B, exactly. Yeah, you're just along for the ride too, right? You don't feel any forces, right? Guys, in physics, is constant velocity and at rest, are those basically physically identical? Yes, they are. Yes, they are. Right. For example, are you at rest right now? Yeah, you're at rest right now. Wait a minute. Or are you? If you said no, I think you're also correct. Or are you spinning along with the Earth almost 1,000 miles an hour to the east? Yeah, and those are physically identical. You cannot feel the difference. All right. All right, ready for next slide? Next slide. Here we go. Air hockey time. Air hockey puck. You guys ever played air hockey? You put that little plastic puck on a table, got those jets of air, holding it up. So this is my go-to example for a frictionless surface. Sometimes I'll say air hockey table, and I'm referring to a frictionless surface, a surface with no friction. So are you guys writing in your notes right now? That scenario, right? Air hockey puck, constant velocity, right? And then you go ahead and draw that air hockey puck. You guys see a big old center of mass dot right there? Go ahead and draw the center of mass dot. Right, so you guys got all that. Right? Now I gave you guys a velocity arrow just for context. Say it's moving horizontally. But the important thing is it's moving with constant velocity. That'll tell you something about the forces that are acting on it. Right? So constant velocity. Well, I know a little bit about the story then. I know it's not while you're striking it with the paddle. So guys, are you guys going to draw a force on it that's striking from a paddle? No, because that happened in the past. Right? That would not be constant velocity. Right. So somebody struck it with a paddle. That was a force, but that already happened. Now the puck is in motion and it's just coasting along the table. You guys got that? Right. And that's what we're looking at. We're just watching this puck go at constant velocity, just coasting across the table. Right? Right. You guys got that? All right. Here. I'm going to walk around the room and check you guys' notes. I want to see who's able to figure out what does the free body diagram look like before I reveal the answer. Just like with all these slides, if you guys can get the answer before I reveal it, then that's a good indication to you and to me that you can critically figure these out. You can think critically and figure out how these diagrams work. Right? What forces are acting on that puck as it's sliding it, as it's moving at constant velocity across that air hockey table surface? Right? Here's a little hint while you guys are still figuring this out. A little hint. Guys, constant velocity, what is the acceleration equal to? 0. Therefore, what is the net force equal to? 0 newtons. You guys think if there's some forces, they probably all cancel out? You guys think all the forces cancel out? They'd have to for constant velocity, right? Constant velocity could be equilibrium. All right. All right, you guys ready for the answer? All right, what's one force you guys drew on this air hockey puck? Yeah, so it's got a gravitational force. It's got a weight pulling it down. There's I connected the tail of the vector to the center of mass dot. You guys see that? Okay, pulling straight down. Now, if you just drew that and walked away, would you be implying that you just tossed it off a cliff and it's in free fall? It's in free fall. Great. But that's not what's going on. Okay, this is sliding across the surface. It's moving across the surface at constant velocity. What other force did you also draw acting on that air hockey puck? Is there something holding it up? Aha, the air jets. The air jets. That's what's holding it up. Okay. Force from the air jets. Okay. Do those two forces zero out? Yep. Okay, so is that air hockey puck in equilibrium? Yep, it sure is. It's an equilibrium. If you were a ladybug that landed on that air hockey puck, and you close your eyes, could you tell the difference between it being at rest or being in motion at constant velocity? Nope, you can't tell the difference. Right, they're physically identical. So, are there any other forces on that puck right now? Are there any other forces? No, there are not. That's it. That's the only two. Are you done? Right. Notice if I did not draw that velocity arrow, it would be ambiguous as to which direction it was even moving. And again, if you're the ladybug landing on it along for the ride, you don't even know if it's moving or not. Right? But I guess relative to the outside table, you'd say, oh, I guess it's moving to the right. Right. Next one. Ooh, the Earth and the Moon. So this is two separate diagrams, one for the Earth, one for the Moon, although they're interacting with each other. Right? All right, so go ahead, in your notes, write three body diagram, Earth and Moon, draw the Earth, draw the Moon, some distance between them. Right. So go ahead, draw the free body diagram for the Earth, draw the free body diagram for the Moon. And while you guys are figuring that out, maybe I'll throw some hints at you guys or add to the story a little bit. Guys, is the Earth pulling on the Moon? Yeah, yeah. I think Isaac Newton figured that out, and that's eventually going to lead to orbits. We haven't talked about orbits in the class yet, but this is going to be a setup eventually for that. For today, we're just focused on the forces. Yeah, there's a gravitational force. The Earth is pulling on the Moon. Is the Moon pulling on the Earth? Yeah, isn't that how tides work? Right, we'll talk about tides also, but you guys probably learned about tides maybe. So, guys, are there two tides every day? Two tides, is that right? Because the Earth spins faster than the Moon is revolving around us. Earth spins once every day. Moon revolves around us, takes a whole month. That's where the word month comes from, right? M-O, moon, month. Right. So you guys got a gravitational force on each of those, right? On the Earth, on the Moon. Now, guys, which force is bigger? The Earth pulling the Moon or the Moon pulling the Earth? The same? The same? Ah, there's Newton's third law of motion right there. It's the same force. Yeah, gravitational force. The Earth pulls the Moon pulls the Earth with exactly the same force. Right? Now, the effects are in motion are different, right? Because guys, why is it that no, the Moon is definitely revolving around the Earth. That's definitely some kind of huge change in motion. Okay. But the Earth, it wobbles a little bit, but it's kind of hard to tell. Why is that? Because the Earth has so much more mass, so much more mass. So therefore, so much more inertia. Okay, but it's the same force. It's the same force. Right, ready for the next one? Next one. Ooh, right. This is one of three. We're gonna do a few roller coasters. Go ahead, write your notes. Free body diagram, roller coaster. Let's start at the top of the hill. Okay. I'll add to the story a little bit. Let's say the coaster is just at rest, or either that or moving extremely slowly. Right, so it's just up there. You guys ever been on a roller coaster? It goes like tick, 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 right before it plummets. Right. Let's say we got that going on. So it's basically at rest. Right. Build some anticipation. Like, oh, I'm ready to crash. Do you guys see the shape of that track? I got a hill, I got a valley, I got a vertical loop. Go ahead and draw all that. We're going to do all three parts, one at a time, of course. All right. So that coaster at the top of that hill, what's one force you guys just drew on that coaster? Does it have a weight pulling it down? Okay, so let's go ahead and throw a weight on the board. So mg could be the weight of the coaster, weight of the cart. Okay. But it's not in free fall. So what other force is acting on it? What's holding it up? The track. Right. And that because that surface force has a name. Anything that's at rest on a surface, what's it called? It is perpendicular. What's a synonym for perpendicular? Starts with an N. Normal. You guys remember normal, right? So normal force. Yeah, that's true. Normal means perpendicular. That is true. Because if the track itself is pretty horizontal at that point, then it would be it would be supporting straight up, which is perpendicular to that surface. Hence the word normal. So normal force. Okay, see that? Right. So there you go. Okay, so that could finish that one. While you guys are finishing that in your notes, I'm going to add to the story a little bit. Right. What if the cart was not at rest at the top of the hill? What if it's flying over, like whizzing over? Zoom, zoom. Let's go a little faster. Zoom, a little faster. Zoom, a little faster. Zoom. Do you think if you go fast enough at the top of that hill, at some point you're gonna like fly off the hill? You're going too fast. Do you think there's like a maximum speed that you don't want to go any faster than before you fly off? Right? Okay. Well, one day we're gonna solve for that. We're not quite ready yet, but I'm just setting up for the future. Okay. How about this? As the cart goes faster, and if you go too fast, it's gonna fly off. How would these forces be changing? Like, would the weight be changing? The weight wouldn't be changing. Right? What about the support force from the track? As you go faster, and eventually fly off. What is this getting bigger or smaller? It's getting smaller. Okay. If you were along for the ride, if you're going over too fast, Do you feel kind of light or kind of heavy? If you're sitting in that cart, you feel really light. That's true, right? You feel really light. Right. So, like, guys, what if you're sitting on a bathroom scale? It's like, okay, I normally weigh. I'm just gonna make some notes. Suppose I normally weigh 100 pounds. Just nice round number, 100 pounds. But you're flying over that top. If you're at rest, that scale also reads 100 pounds. Is not true, right? But if you're flying over the top really fast, you think maybe that scale only reads like 80 pounds? Right? Like it went down a little bit. Right. Hold on to that idea because in a few weeks that's going to come back. All right, next slide. Now we plummet down to the bottom of the valley. Now, guys, in your notes, make sure you draw the bottom of the valley as a curved path. You guys see that being a curved path? Right? We haven't talked about being on a curved path very much in this class, but yeah, this is set up for the future concept. But today we're just focused on the forces that's eventually going to open up a wider story in the future. So that cart is moving forward. Right, I've got a for velocity vector just to remind you guys that this cart's in motion, although it's not part of the free body diagram, but it is important context because if that cart is moving forward, is that track also forcing it up into the loop? Do you guys think forcing it up into the loop? Right. Okay, so it's trying to just move forward, but I think that track, the fact that it's curved, is going to force it up into a loop. Right? Go ahead and draw the forces acting on that cart of that motion for that situation. The cart's moving forward, but it's on a curved track, so it's eventually going to be forced up into the loop because it's on a curved part of the track. Right? What forces are acting on that cart? Right? Now, I'll give you guys a little hint while you guys are trying to figure this out. Suppose you're along for the ride. Do you, at that moment, going really fast through that valley, do you feel really light or really heavy? Heavy? How many of you guys think heavy? Heavy? I think you're right. I think I would too. Like, again, normally if you weigh, say, 100 pounds and you're sitting on a bathroom scale, do you think that scale probably reads like 120 pounds? Probably? Yeah, I think it would. If you're blindfolded, it's like, wow, why do it feel so heavy? Huh. Great. Hold on to that idea. I'm going to probably about a month from now, have you guys do a lab where you derive an equation that can tell you exactly how heavy and how it's related to the curve and how fast you're going. There's an equation that links it all together. Right? But today, forces. Do you guys draw some forces? Because what's one force you guys drew on that roller coaster cart? Weight. It's definitely got to weight, pull it down. So throw that one on the board. That's the same weight as before, isn't it? Same weight, same gravitational pull. Okay. Right. Now, here's a little bit tricky one. What's the other force also acting on the cart? Is the track supporting it? Right? Okay. How much compared to the weight? Huh? Remember, if you normally, if that cart was at rest, suppose it weighed 100 pounds, but now it's in motion. Zoom. Is that scale rating 120 pounds? Because you feel really heavy, right? Which tells you something about how much the track is pushing up. Is it pushing up more than or less than the actual weight? If you normally weigh 100 pounds and it's reading 120 pounds, that would have to be more than, right? Have to be more than? Here's the answer. There's the answer. Yeah. Okay. So it's a normal force from the track. You guys see how I made the normal force longer than the weight vector, right? Because it's more force. It's more force. Right. So while you guys are writing that down, here's kind of the dynamic of how this is going to work. As that cart moves forward, there is a net force on that cart. That net force is upward. You guys see if you do the upward vector minus the downward vector, overall it's being pushed upward. So that as it moves forward, it's actually forced up into the loop. You see that? As it moves forward, it's being forced upward into the loop. Right? Does anybody know what is the name of the force being on a curved path? Starts with a C. Centripetal. Yeah, centripetal. Centripetal force. Right. Now, you're never going to label a force the centripetal force. Right? But it does show up here. I'll show you guys where it shows up. It's the net force. If you do normal force minus the weight, there's some net effect, some net force. That's the centripetal force. That's eventually going to feed it into an equation. That has to do with how fast is the cart moving and what's the radius of curvature. Right. So one day. Right. All right. One more of these roller coasters. Let's go to the top of the loop. So now it's whizzing through that vertical loop. All right. You guys drawing new notes here. New notes. And so now we're at the top of that vertical loop. So of course, today I just want you to draw what are the forces acting on the cart. But I'll throw a bunch of other questions that just going to be sitting around for the next few weeks. But eventually, we're going to answer in this class. Like, how about this? Do you think that there's a minimum speed to guarantee that you get around the loop? Right. For example, what if you had 0 speed at the top? What if I didn't even draw a velocity at all? What would that cart do? It's going to fall off the track, isn't it? That's a bad day for everybody. So okay, so it definitely can't be a Russell there. Right? To get around the loop, it's got to be in motion. I wonder what is the minimum speed. Hold on to that question because we're going to answer that a few weeks from now. Right? Right. Okay, so that aside, let's think about what kind of forces could be on that cart. What kind of forces, right? And maybe a hint could be again the question: what does it feel like? I suppose you're blindfolded. Or has anybody ever been on a roller coaster that's like in the dark? Has anybody ever been on one of those? Right, it's a giant dark room. You can't even see anything. It's like along for the ride, surprise. Right? Here, let's suppose you're in one of those, or maybe you're blindfolded. Right? Oh, suppose you just barely make it around. Suppose it's going just barely fast enough to just barely make it around the loop. What would that feel like at the top of the loop? Would you feel really light or really heavy? Really light. You would, right? In fact, if you just barely make it around, I bet you feel like an astronaut just for like one moment, right? Which is probably kind of dangerous, right? So do you guys think it's probably safer to make it whiz around pretty fast, like faster than that? So you want to go past that. In fact, the faster and faster you go, how do you feel inside the cart? Like heavier and heavier, right? In fact, what if you whiz around really fast? Do you think it's possible you could even feel heavier than your usual weight? That could happen too, right? So depending on how fast you're going around and what is the radius of curvature, you might feel really light or really heavy, right? So it could be any of those, right? So I'm setting up some hints about ultimately what are the forces acting on that cart, right? You guys ready for the forces? You guys ready? Right. Guys, what's one force you guys threw on that roller coaster cart? Okay, so definitely it's weight. Let's throw that on the board. Bam. Okay, so it's got some weight. Okay, let's just trying to make it fall off. Right. What other force do you guys think? Tell you what. If it just barely gets around, that would be the only force. If it just barely gets around, like with the minimum speed, that would be the only force. Okay. But suppose it gets around with sufficient force, like zoom, zips around with sufficient. I meant sufficient speed. That's what I meant to say. Suppose it gets around with sufficient speed. Right? Do you think the track is starting to push on that cart more and more the faster it goes? Right? And what's the name of that force again from the track? No. Normal force. Normal force. Right? Right. So one last detail before I reveal the answer. Which direction did you guys draw the normal force of the track pushing on the cart? Same direction as the gravitational force. It is down. It is down. Right? You guys have not seen this yet in this class. I was curious to say how many of you guys are going to get that. That was a really tricky question. Right? Yeah, the track pushes down on the cart, and the same direction as its weight in this case. Right? Now this is gonna be kind of tricky because well, hold on a minute. If I'm along for the ride, let's go back in the cart. So you're in the cart, you're blindfolded, you're along for the ride. Right? Suppose you get around with sufficient speed, the whole deal. Right? Which way does it feel like you're being pushed as you're along for the ride? Does it feel like you're being like pushed up into the floor of the cart? That's what it feels like is going on. But did I draw any upward acting vector? I did not. Right. I guess from the track's point of view, there's a Newton's third law. The track pushed against the cart pushed back against the track. But for this free body diagram, we're just focused on the cart. Okay? There is no upward acting force, which is weird because if you're along for the ride, it definitely feels like there is. Right? Here's the difference. If you're along for the ride, you're in a rotating frame of reference. So you experience what you could call a centrifugal force, which is a word I'll almost never use. Because all these diagrams we're doing from not a rotating frame of reference, but from an inertial frame of reference. So somebody standing off to the side looking like third person point of view. Right? And from that point of view, there are no centrifugal forces. There's only, well, the forces you see, which are acting as a centripetal type force. So something like that. Right. Hold on to that idea because I got some new slides coming up that are also kind of related to that too. How we're doing on time here. Gotta see. Okay, we're doing good. Car brakes to a stop. Car brakes to a stop. Go ahead, write in your notes. Car brakes to a stop. Draw my little turtle car with my little wheels on it. Car brakes to a stop. And start labeling the forces. What forces are braking that car to a stop? Guys have a thumbnail notes about this one, maybe? Just think. All right. Here, let's get this number. I got a whole story to tell you guys about this that's been coming up today. So what's one force you guys put on the car? It's got a weight pulling down. Okay. Oh, let's suppose we got a flat road. Okay, flat force on a road. What force is holding it up? Is that the normal force holding it up? Okay. Okay. Now, if you just had those two, the car would probably go in constant velocity. But we need to brake this car to a stop. Suppose you're out on the road. Is it easier to brake to a stop on a dry road or a road that's covered over in ice? Dry road is definitely easier to stop. Which might tell you what kind of force is bringing it to a stop. What force? Friction. Friction. There it is. There's friction slowing down the car right there. Right. Here's where I got a whole story for you guys, or maybe you might know this. I don't know. Did you guys get a driver's license recently? Maybe driver's license. When you guys got your driver's license, here's a real question. I don't actually know. Right? Did you have to learn about something called anti-lock braking system, ABS, anti-lock braking? Okay, I'm saying yes, yes, yes. Right. I've been asked this question all day, and it's like half the students say yes and half the students say no. So I don't know what's going on there. But yeah, anti-lock braking system. Let me tell you guys about the physics of this. What it's about. So suppose you get an old car from decades ago. It's like from 1973, and you're driving this around, right, like an old style car, right? And then suddenly you got to stop in a hurry, so you slam on the brake, and do the wheels lock back from 1973? The wheels lock, and the car skids to stop. Right now, a few days ago, I think I mentioned that there's two different kind of friction. Did I mention static friction and kinetic friction? Did I mention that? Right. Because here's the difference. Here's a quick recap. Right. So suppose there's a box, big old box sitting in the middle of the floor. You got to push this box against the floor. So you walk up to it. It's a big, heavy box, and you give it a push. And at first it sticks. And I can't move it. Can't move it. Because what kind of friction is that? Is that static or kinetic? Static. It has not broken the initial friction yet. Now, once you break that initial friction, you get that box moving. Is it easier to keep it sliding than it was to break the initial friction? Turns out it is. Yeah, you don't need as much force to keep it sliding. What kind of friction is that? That's kinetic. That's kinetic friction. The two surfaces are sliding past each other. Right. Okay. So, guys, recap question. Which force again is generally larger? Static friction or kinetic friction? Static. So, to tie this back to this car, if you had to stop in a hurry, would you rather take advantage of static friction or kinetic friction? I'm going with the bigger one, which is the static one, right? Okay, now let's think about what the wheels are doing. You guys remember that car from 1973? You slam on the brakes, the tires lock, and it starts skidding. Wait a minute, that's kinetic friction, isn't it? That's not the one you want. That's not as good. That's not as good. Right. The old advice, if you like go back in time, the old advice used to be this: don't actually slam the brakes. You actually want to pump the brakes because that'll rotate the tires a little bit, and that'll help you maintain traction. Right? But that's not the advice anymore. Don't do that anymore. Right? Because if you have a modern car from 20, whatever it is now, do you actually want to go ahead and slam the brakes nowadays? Yes, you do. Because in your car is a computer system called anti-lock braking system, and it'll take over. And what that'll do is it'll very slowly rotate the wheels forward as you're braking to a stop, and it'll like calibrate with the road and whatnot, because it's trying to maintain traction with the road. It's trying to take advantage of static friction, right? So by rotating the tires forward a little bit, it actually stops the car faster than if the wheels had locked, right? But let the computer system take care of that. That's anti-lock braking to take advantage of static friction. All right, next slide. Car goes around a curve. Let's say, see that block right there? Suppose that's a car. Can you guys see a couple of tail lights? Is that car in front of us has a couple of tail lights on it? Let's say this guy's making a left-hand turn. I should have written that. Can you guys write in your notes? The car in front of you makes a left-hand turn. And we're gonna do a free body diagram on the car in front of you making a left-hand turn. Go ahead, write the scenario, draw a little boxy looking car, maybe draw a couple little tail lights on it. So you guys know you look at that, maybe draw a little license plate. All that going on. The car makes a left-hand turn. All right. I bet you guys have figured out at least a couple forces already. What's one force that has to be acting on the car? Pulling straight down? Yeah, so weight, gravitational force, weight. So I'm doing mass times gravity field, call it mg. Going along. Okay. Oh, hold on a minute. What's keeping the car up? Normal force, right? Actually, this is assuming a flat road. I meant to mention that detail too. So let's say we got a flat road. And if we do have a flat road, how is the car able to make the turn? How about this? Guys, is it easier to make a left-hand turn on a dry road or a road covered in ice? Definitely a dry road, right? Like if the road was covered in ice, it'd be really hard to make the turn, wouldn't it? Right? So dry road is easier. Okay, what I'm trying to get at is what force is actually allowing the car to even make the turn? Friction between the tires and the road. Can you guys draw a friction force? Now, guys, if you're making a left-hand turn, which way is the road pushing the car? To the left, right? Now, this kind of ties back to a situation a few slides ago with the roller coaster, that you're on some kind of curved path, right? Where if you're inside a car, suppose you're inside a car and you sit a tennis ball down on the back seat. You guys imagine that? Tennis ball on the back seat? And you make a left-hand turn. Which way does the tennis ball appear to roll relative to the car? To the right? Does it look like it's going to the right, right? That would be true, right? Now let's switch perspective, because that's inside a rotating frame of reference. You're moving along with turning with the car. Right? Let's go into helicopter. Can you guys imagine we're a helicopter? Looking straight down, we see an open top car. You guys see that? Looking straight down on this car. Right? And I say, oh, hey, there's a tennis ball in the back seat of the car. You guys see the tennis ball in the back seat of the car? Looking straight down from above. Right? And now that car makes a left-hand turn, turns left. Right? Guess which way that tennis ball continues to move? In a straight line. In a straight line. Is that called law of inertia? Law of inertia. Right? From our point of view in the helicopter, looking straight down, that tennis ball only moves forward in a straight line. The car makes a left-hand turn. So if you're sitting in the car, you think the tennis ball is going to the right, but it's really not. It's really just going straight, and the car's going to the left. You see that? Right? Now, that story I just told you, it'd be really nice if I had an animation. So I do know where there is one. Did you guys know a YouTube channel called Vsauce? Vsauce? Okay. When I upload this video to Google Classroom later, I'm also going to include a link to a video called Spinning from Vsauce, where he covers that story, and he sets up some physics that's going to show up in this class a few weeks from now. So you guys get a little preview. Okay. Let's see a few more of these. A few more. Right. Block hanging at rest from a spring attached to a ceiling. Actually, I might go a little faster with these because I want to show you guys a walk time video today too. It's about 5 minutes. So here we go. We did this one the other day anyway, didn't we? Right. Guys, what force is pulling down on the weight? Yeah, gravitational force, mg, so the weight, right? What force is holding it up if it's on a spring? Is that a spring force? Spring force? I can just label that spring force, right? And if you wanted to go one more step, that spring force is equal to what times what? F equals kx. F equals kx. Could that be Hooke's law? You could also label it that, because F equals kx, right? All right, and also that's a poster here, I think, right? You guys see a poster? All right, next slide. Next slide. Bottle rocket blasted upward through the air. Let's bring in air drag. Why not? Right. So, do you guys think the rocket fuel is blasting out the bottom of the rocket and it's blasting the rocket forward, up, right? Up, right? Okay, so you got a little Newton's third law there, right? The rocket fuel goes down, the rocket goes up, right? But we're just going to focus on the rocket. You guys think there's probably here? I'll just go ahead and throw these in here. Right. Do you guys think the thrust force is blasting the rocket forward, like up? Right. I got maybe a weight pulling back the other way. And one more. Do you guys see a poster in my room that says drag force with a parachute on it? You guys see drag force? And there's an equation at the top. You guys see F drag equals, and it's a big old equation. And at the very end, it says V squared. So the drag force turns out is proportional to the square of the speed. If you're going 3 times as fast, you got 9 times the drag force, kind of thing, right? Okay, so if this rocket's going through the air, I bet the drag force is going to oppose that, proportional to the speed squared, something like that. All right, you guys good with the rocket? All right, see what I got next. Ball flying through the air. Oh, hey, did we do this one earlier today at the beginning of the class? Didn't we do it for the cannonball flying through the air? Like we took those cell-phone pictures. Did, right? And guys, what force do you have to label on something flying through the air? Yeah, gravitational force. That's really the one that matters, right? Right. That's the most important one. If there's no air drag, is that the entire story? Yep, that's it. Right. Now let's go ahead and bring in air drag. See where it says in parentheses, there is air drag. Okay. Guys, if there's air drag, which way does the air drag always point? Opposite of the motion, right? Now, these two forces right here, while you guys are finishing writing that, the weight is, that one's easy. That one's the same the entire flight. If this is a 10 Newton ball, it's always 10 Newtons. Guys, the drag force, is the drag force constantly changing direction as the ball changes direction? It is, right? Also, as the ball slows down on the way up and speeds up on the way down, is that drag force get smaller and bigger with the ball speed? Yeah, that's also true. So this drag force is really, really tricky because it changes direction and it also changes magnitude as the ball flies through the air. But the weight's just real straightforward. The weight's just always the same. Okay. All right. I think I just got a couple left here. Two people pull a stubborn donkey. And if the donkey is not moving, guys, not moving, what do you know about the net force if it's not moving? Zero Newtons, because that would be an example of equilibrium. Either not moving or constant velocity, either one of those are both zero net force, right? So is this guy pulling up to the left? Is this guy pulling up to the right? So there's a couple of tension forces there. And if the donkey's not moving, what other force must there also be to keep the donkey at rest? You think the donkey has his hooves dug into the ground? I'll go ahead and call that a friction force. Could that be kind of like that? Right? Now, if I do this exactly right, I think I kind of close. Right? Guys, suppose you introduce a Cartesian system. You got forward and backward, and I got right and left. Right? Is this guy pulling left as much as this guy's pulling right? Yep. Is this guy pulling forward plus this guy pulling forward as much as the donkey's pulling backward? Yep, that should also be the case, right? For zero net force, everything zeroes out. Or you can connect those three tip to tail and they'll still zero up. All right, here's the last one today. Here's a new situation. We're going to do a bunch of these, but at least I'll introduce this to that, you guys, before the weekend. A block on an incline. Now, block on an incline. Guys, is there a weight pulling the block straight down? Go ahead and draw a weight pulling straight down. So we got that. Okay. Now, the rest of this puzzle, I could throw you some numbers. I could throw you how many degrees is the incline. I could give you a mass number if I wanted to. I could ask any number of questions about this. If you want to do some mathematical analysis, the rest of this puzzle, I'm going to introduce a Cartesian system that runs parallel and perpendicular to the surface. I'm going to think in terms of that. You guys see a couple of pink lines pop up? Is parallel perpendicular to the surface? Is that? Okay. I'm going to rewrite this weight in terms of those rotated axes, right? So can I break out a sine and a cosine? Right. You guys think this angle theta is always exactly equal to this angle theta? You guys think? If this is 29.5 degrees, is this also 29.5 degrees? How many of you guys say, yep, that would be the case, right? Okay, so there's the components of the weight. Notice I dashed them, right? Okay, guys, what force is supporting the block holding it up? What is that called again? Normal force, normal? And what does normal mean again? Perpendicular? So are you guys going to draw the normal force straight up or perpendicular to the surface? Let's go perpendicular. That's what normal force is. Normal is perpendicular. See it's going perpendicular, right? Did you guys see that normal force is not pointed straight up? A lot of students miss that. See it's kind of off to the side. It's perpendicular to the surface. Right? One last thing. If I stopped there, I bet that would be accelerating down, kind of like your car in incline lab. Does it look like a Hot Wheels car that's actually accelerating with a net force of mg sine theta, right? But if I want to block at rest, what force is holding it in place? Friction. And which direction do you draw the friction force? Bam. So do you guys see those three forces exactly zero out? They exactly cancel out. Looks like my normal force is canceling out the mg cosine theta. Looks like my friction force is exactly canceling out the mg sine theta. Right? So all three forces cancel out. Aha. Is that too? Right. All right. And that'll take us to the weekend right there.